Now that we have some theory and some methods that are related to linear systems, we're going to take a look at how linear systems themselves can be applied to solve other problems, right? And that process is not new, or it shouldn't be new, in your math classes. For instance, think about calculus. You learn how to find derivatives, and then you learn how to apply them. Then you learn how to find antiderivatives, and you learn how to apply them. So it's, now that we know how to solve linear systems, maybe we can look at some ways that we can apply them to solve other problems, right? And we'll do this over a series of videos. And this first video, there is not like a single name or a single type of applications. We're actually going to look at three that are very different, but they all involve setting up a linear system. But they're not of one particular type. So let's just call these general applications. And these are those lovely story problems that I know everyone loves. So general applications. So what I have, so I'm going to scroll down and bring up the first one. And here is the first one. And I will have to change my ink color. Okay, there we go. So let's read this one. So this is a problem, it's a mixture problem, right? Mixing a solution. So we have a chemist who wants to make 14 liters of a 40% acid solution. And she has solutions that are 30% acid, so that one's a little bit less than what she wants. And then she has another one that's 65% acid, so that's a little more than what she wants. So then the question is, how much of each of the 30% and the 65% must the chemist mix in order to get the desired 14 liters of a 40% acid solution, right? So everyone clear, right? So we have 30% of one mixture that's 30% acid, another that's 65% acid. How much of each should we mix so that the resultant mixture will be 14 liters of a 40% acid solution, right? So what's unknown is how many liters of the 30% and how many liters of the 65%. And what we're going to do, and this will be the case for each of these story problems that we're going to look at, we will set up the linear system, but I am not going to solve. In fact, I think I'm going to leave it as kind of an open problem that you can solve and maybe even, submit the solutions for some points. All right. So let's first define some variables. So let x represent the number of liters of the 30% solution. All right, so that's how many liters of the 30% solution we're going to use. And similarly, let y represent the number of liters of the 65% solution. All right. So since there are two unknowns, right, we need two equations to even possibly come up with a unique solution for this problem, right? So we have to have two equations. So let's see. Well, first, we know how much of this mixture we want. We want 14 liters, right? So therefore, when we take the number of liters of the 30% solution and the number of liters of the 65% solution, when we mix them together, we should get 14, right? Well, mixing them together is just addition. So here's our first equation. X plus y has to be equal to 14. This equation represents the desired volume, right? That's what we want. This is the desired volume. We want to get 14 liters of. Now, let's look at the other requirement. The mixture should be 40% acid, right? So that means if I take the number of liters of the 30% solution, that will contribute, well, X times 30%, right, of acid, right? And plus, again, similarly, when I take this number of liters of the 65% solution, it will contribute 65% of that amount of acid. But what we want is we want to have a 14 liters of a 40% acid solution. So we want all this sum here must be equal to, right, the 14 liters times the 40% acid solution, right? So this, and essentially that the 14%, the 30%, and so forth, that's pretty much a concentration. So this here represents the desired concentration of acid, right? I run off the page here, concentration, right? So the first equation satisfies how much of this acid we want, the 14 liters, and then the second equation satisfies the requirement in terms of what is its concentration, right? So in terms of the system, I mean, I think we can see it, but let me write it in the typical form. So here's our system. We have X plus Y is equal to 14. Convert each of the percentages into a decimal. And then, so this would be 0.3x, that's the 30% as a decimal, plus 0.65y. Again, that's the 65% as a decimal. And then just take 14 times 0.4, and that's going to give us 5.6. And this is the linear system whose solution will tell us how many liters of the 30% and how many liters of the 65% we need to get what's desired, right? So as I said earlier, I'm not going to solve these. I'm just going to set them up, and then I will leave it to the viewer to solve. And talk to me, and we can figure out an arrangement where maybe you'll earn some extra points by showing me that you've solved these correctly. All right. Okay, so that's our first example, and this is of like a mixture problem. Now let's look at the second one. So I'm going to scroll on down, and let's see what we have. Now this one is a question about computing wind speed. All right, let's see what this is all about. It says, with a tailwind, a small Piper aircraft, so that's a type of airplane, it can fly 600 miles in 3 hours. So that's when it's going with the wind. So that's the tailwind. So the wind is pushing it a little faster than it's actually flying, right? And it can fly 600 miles in 3 hours. If it's going against the wind, the Piper can fly the same distance, but it's going to take an additional hours for a total of 4 hours, right? Our goal is to find the average wind speed, so actually how fast is the wind blowing, and the average air speed. How fast is the airplane flying, right? So again, let's define some variables. So what are the two things we want to find? We want to find the plane's average airspeed and the average wind speed, right? So let's use x to represent the plane's average airspeed. So this is the plane's average airspeed, right? And that's one of our unknowns. And then we also want to know how fast is the wind blowing. So that would be the average wind speed. Now, we're looking at averages. So one thing we can assume here is that they're both constant, right? If we allowed for variable wind speed, then that's where we need calculus, because then we would go from average, rates of change to instantaneous, right? And then it would be really fun. But right now, we're just going to assume that things are constant, and let's see what happens. So to organize this, I'm going to set up a table. So I'm going to have a column that has the rate, so that would be the speed. And then another column for time, and then another column for distance, right? Because these are all the three quantities that are given to us in this problem. The rate, that's the speed, right? Which we don't know, and the times are given, and the distances, well, it's one distance. The distance is given. And let's write down the two scenarios. With the wind, so let me take this off here. So with the wind, and then I'll fill out that row, and then let's do against the wind, and then we'll fill out that second row. Wind. All right, so what's the rate? Well, when it's with the wind, these two are working together. So because they're basically acting in the same direction. You have the wind, that tailwind, which is pushing the plane. So the overall rate or speed would be the sum. This would be x plus y. And we were told when it's flying with the wind. Wait a second. Why did I use? Oh, I used with. Again, I was thinking geometrically. This is with, W-I-T-H. Man, that was embarrassing. All right, so that's our rate, x plus y. And then with this speed, it takes the plane 3 hours in order to fly 600 miles. Now, when it's against, so it would be, so the plane would be going in one direction and the wind would be going in the opposite direction. So that opposite direction would have a net effect of reducing the plane's speed. So that would be x minus y. And it takes now 4 hours with this reduced speed to travel the same distance. All right. So again, this table, right, having defined these variables, this table is just a summary of the words that were given in this paragraph, right? So we haven't really done anything. But what relationship do we know what is the relationship between rate, time, and distance? Well, there are different ways that relationship can be expressed. You could say that the rate is equal to the distance divided by the time. And that's fine, right? But when you think about our so we could set it up like this, or another way you could set it up. You could say that the rate times the time is equal to distance, right? And again, I just want to point out that these equations are true when you have like constant speeds and so forth, right? So either one we could use. I'll go ahead and use the second version with that involves the product. So basically, to set up our equation now, if I take this entry that's in this first column and then multiply this entry in the second column, it has to be equal to this entry, right? So what we have is this, x plus y times 3 is equal to 600, and then similarly x minus y times 4 is equal to 600. Now we could distribute the constants and have 3x plus 3xy, I'm sorry, 3x plus 3y and 4x minus 4y. But since our goal is to solve for x and y, it's probably easier to divide both sides. So then, and you notice if you divide both sides, you end up with this form of the relationship, right? So you'll have x plus y, dividing both sides, the first equation by 3, you'll end up with 200, and then dividing the second equation by 4, you'll have x minus y is equal to 150, right? And that's a really simple equation to solve, but my offer still stands. You solve this and submit your problems, and again, we can talk about deadlines and so forth. Just contact me, have your people call my people, and we'll work something out. But there is the linear system, a really simple linear system that when we solve this system, it will allow us to determine the plane's average airspeed and the average wind speed. All right, nice little application there. And again, these are problems that you could have been introduced to them the moment you first learned about linear systems. You could do a whole chapter on these types of problems, and in some cases, it is done like that, right? And that's why I call them general. There is no specific formula to say, okay, you always do this. It's just analyzing the situation, thinking about what it is you're trying to find, and then looking at the relationship between the variables and the constants, right? And obviously, since we're talking about linear systems, that relationship will always be a linear one. Okay, so like as I promised, we have 3 of these. Let's look at the third one. Man, that's a lot to read. Okay, so it's a nutrition problem. So a dietitian wishes a patient to have a meal that has 66 grams of protein, 94.5 grams of carbs, and 910 milligrams of calcium, right? So that's the desired outcome of having this meal. And then food service tells the dietitian that the dinner today is chicken, corn, and 2% milk, right? And then it says each serving of chicken has 30 grams of protein, 35% carbs, and 200 milligrams of calcium. And then the similar information is given for the corn, like how much protein does the corn have, how many carbs, how much calcium, and so forth. And then finally, the 2% milk, right? So the assumption is you're going to have this meal of chicken, corn, and 2% milk. And then the question is, how many servings of each type of food should the dietitian provide to the patient given the desired outcome of 66 grams of protein, 94.5 grams of carbs, and then 910 milligrams of calcium, right? So what we are required to find is the number of servings of corn, chicken, and the 2% milk. So since those are the things we have to find, let's go ahead and define them, right? So we're going to let x represent, let's say x represents the number of servings. Let's start with the chicken. And then let y represent the number of servings of corn, right? Lovely corn. And then again, since it's now 3 unknowns, but we're gonna have to jump up to our letter z. So let z represent the number of servings of the 2% milk. All right. So what it says each serving of chicken has 30 grams of protein. So if I take X number of servings times the 30 grams, that's how much the chicken would contribute to the protein. So let's write this down. So if I take 30x, that's the amount of protein that I would get from this number of servings of the chicken. Let's look at the corn. Corn doesn't have that much protein. It's only 3 grams per serving. So y times 3, so if I now add the corn to my meal, so 3 times y, and then finally let's look at how much protein is in one serving of the 2% milk. Well, it's 9 grams. So if I take 9 grams times that number of servings of the 2% milk, then in total I want to get 66 grams of protein. So this will be equal to 66, right? So this is the amount of protein in the number of servings of chicken that I'm going to have. This is the same for the corn that I'm going to have, and this is for the milk. So basically that first equation, right, is to make sure that we get the desired protein, right? Then let's change to the carbs, right? Well, yeah, carbs. So the carb equation, so let's see, let's start with the chicken has 35 grams of carbs. Really? That much? 35 times my x plus, and then let's see how much carbs in the corn. 16, that makes sense. So 16y, and then in the milk, 13 times z, that will be equal to, and we want that to be 94.5. Again, so that second equation is the desired amount of carbs. So this is the desired carbs, right? And then finally, we want the calcium. So we would expect the milk, based on what the lobbyists in Washington tell us, milk does a body good. Well, you should have me talk about it someday. It's not quite as good as they make it out to be. But anyway, I digress. So let's take a look at, so for the calcium, in the chicken we have 200 milligrams of calcium. Again, that's a little more than I would have thought, but 200x plus, and then let's look in the corn. It has 10 milligrams of calcium, so 10y there. And then finally, this is going to be a big number, yes, milk, 300 milligrams of calcium, and it's 300 times z, and we want the desired amount of calcium is 910 milligrams, right? So again, that third equation, third and final equation, will give us the desired calcium, right? And that's our system. Again, I think it's beautiful when you look at this stuff and you have this paragraph that you have a lot of numbers and stuff like that, but then you distill it, and what you see when we do stuff like this, what we're doing is we're creating a mathematical abstraction of a real life scenario, if you will, right? And this mathematical abstraction now we can solve and then go back and say, hey, here's the answer to your problem, right? And again, this one circle, I'm not going to solve this. Looking at it, you can see it's gonna take a lot of work, but this is another one that you can do, and you can submit it for some extra points. Just let me know if you're interested, and we'll figure out a process, right? So hopefully you found those interesting. I came up with different types of applications just to show you the diverse, that there's not, you can't just put them in a certain box and say always do this. You really have to read, analyze, and like I said, abstract, and then figure out the relationship amongst everything. All right. Well, I will see you in the next video.